Hi, my name is Lars Rönnbäck, and today I will be talking about a philosophy of modeling, particularly with respect to what later becomes transitional modeling. So let me just back up a little bit first. All of this began quite a long time ago when back in 2005, when I and a colleague were asked to create a enterprise data warehouse at a Swedish insurance company. And they wanted a technique because of some of the previous data warehouses that they had had experience with. They tended to become quite expensive to maintain over time, so they wanted to try to build something that would have a low maintenance cost and a long lifetime. Incidentally, later on, I actually read a study that was made in the United States where they looked at 450 data warehouses. And in that study, one of the things they looked at was the average lifetime of a data warehouse. This was done quite a few years ago, though, but I think it was in 2009 or something. But what they found was that the average lifetime of a data warehouse was about 4.5 years. And in my opinion, that's way too short. I mean, building a data warehouse is quite an investment. And on top of that, you also have to put some dedicated resources into actually maintaining the data warehouse afterwards. So it's quite expensive to actually have to redo this data warehouse every, say, 5 years or so. So what we came up with back then was sort of the precursor to what is known as anchor modeling today. And to the best of my knowledge, they are actually still using this data warehouse at that insurance company some 15 years later. So that should be a sort of a testament to that the technique actually works. So with anchor modeling, we were able to create a modeling technique that was quite flexible and could adapt to changes without spending too much resources in doing those adaptations. So people will probably recognize me from being one of the inventors of anchor modeling. And apart from that, I have my own consultant company, a small one called Up to Change, where I do consulting for different companies in Sweden. Now, once we had built that data warehouse at that insurance company, we went on and built a couple more at other companies, and we started to realize that this thing, anchor modeling, was probably something that others could benefit from as well. So we decided to present the technique at the Data Warehousing Institute in 2007 in Amsterdam. And of course, we got a lot of tricky questions. Some of them we couldn't even answer at the conference. So when we came back to Sweden, we contacted Stockholm University and the Department of Computer Science. And we said that we have this new modeling technique and we need to put it on more firm ground so we can answer really tough questions. And are you interested in helping us? And they were really interested, thankfully. So ever since 2008, we have been doing collaborative research in information modeling. So I'm doing part-time research on information modeling. And the presentation today is going to talk a little bit about what I've discovered in that research. Lately, to begin with, it was much focused around anchor modeling in particular. But as we were extending anchor modeling and doing new papers on new formalizations and things like that, we discovered that there was actually in the formalization the basis for a more fundamental way of thinking about modeling. And that later on became transitional modeling, and that is sort of my focus right now in research. So transitional modeling is a more fundamental modeling technique. And we're going to see today how we can actually express anchor modeling and semantic triples using this technique. But it doesn't stop there. I could express third normal form or data vault or something like that as well. Okay. So let's start by looking at some of the philosophers that have actually influenced this technique. So we're going to start with Leibniz. You know, back in the day, most people were quite multidisciplinary. So he was not only a philosopher, he's a mathematician, etc., etc. So one of the things, anyway, he said was that no two objects can have all the same properties. And this is the basis, actually, for what we will call identification. And identification is a very important concept within information modeling, because you need to know when you see something, if it's something new or if it's something you've seen before, because the actions you will take depending on those two scenarios are quite different. If it's a new thing and you want to store it in a database, you can store it as is, assign a new identity and store everything about it. If it's something you've seen before, well, then maybe you want to check if anything has changed and store information about those changes instead. So it's quite different logic. And of course, identification is also important when we talk about what constitutes actually, what does it take to become a thing in its own. So the way that we actually tell things apart is by them having at least one property that separates them. So we tend to notice these differences, and through those differences, that's the way we actually tell things apart. And that's why I wanted to have this quote at the beginning of the presentation. So the next one is an older one. This is Heraclitus from the old Greeks. He has a lot of great quotes. One of them is "everything flows," but he also said you cannot step into the same river twice. I think he also said the only constant is change. So basically his philosophy was centered around the fact that everything around us is in constant flux. So if you look at things surrounding you, they will be changing continuously all the time. So that of course complicates matters if you want to store information about reality, because reality is not this thing that remains static. It's this thing that is where every part of it is constantly changing. So change is very much at the core of reality, and of course that is something that we have to reflect if we want to capture information about reality. So how do we then go about to actually do that if reality is this hard to capture thing because everything is constantly changing? Well, there's this Buddhist theory or philosophy that dates back to Vasubandhu. He wrote about it in the Buddhist doctrine of momentariness, and he says that all things are momentary. And basically what he means is that the things that we perceive as humans, we don't perceive in a continuous manner. It's more discrete, it's moment to moment. And this is something that we can actually make use of if we want to capture information about this ever-changing reality. We sort of look at reality as a snapshot to snapshot, in a snapshot to snapshot manner. So you take a snapshot and you look at reality and capture information about that snapshot. Then some time passes, and then you look at reality again, and then you capture information about what it looks like at that moment in time, perhaps documenting changes, etc. So this is an early documentation of sampling, like if you have music like an orchestra playing and you want to put that onto digital media, you would use something called sampling. And that's exactly the same thing. You capture where the waveforms, the levels of the waveforms at a certain frequency. So moment to moment. And that's precisely the way we can actually deal with this ever-changing reality as well. And if you are creating information models, you have to figure out what your sort of granularity will be, or your frequency, how often are you going to be sampling or creating these snapshots of reality. Then we have Heisenberg, a famous physicist. You may know him from the Heisenberg uncertainty principle. And he said that the reality we can put into words is never a reality itself. And I think this is also a very important aspect of information modeling, because when we capture information about reality, it's impossible for us to capture everything. And of course, if we are going to document reality, we have to do it using some sort of language or syntax. And this in itself is restricted in its expressiveness. So that means that not only are we translating reality into a different language, we are also compressing reality. We lose the fidelity of reality in the language we use to express it. So we cannot really, the only way to recapture a moment completely would be to sort of rewind the universe to that point in time, which is of course impossible. So we have to tell a story, and we have to tell it as good as we can. But that story will of course never be reality itself. So when we build information models, we also have to take this into account, that it is a huge simplification of reality, whatever information we decide to store. And this is also important when you look at the use of the information later on, because the people that are going to use the information, what types of associations or what types of mental images will they get when they see this information? Because they will try to recreate what they believe reality actually looked like from these descriptions that you have, or the stored information. Bertrand Russell, famous philosopher, he said that some things are more nearly certain than others. So if we now accept the fact that we, from moment to moment, capture snapshots of reality, and we compress this into some sort of language where we lose a lot of fidelity when we describe this, whatever it is we're describing in reality, then of course there's also the case that we cannot be absolutely sure about everything that we capture. And usually when you look at information in databases, we tend to treat that information as facts. But we have to remember that whoever put that information there is not infallible, or we can't measure anything in infinite precision. So there will always be uncertainty in the things that we actually capture and store in a database. And wouldn't it be nice if we could actually express this uncertainty somehow as well? Because very, very few actual modeling techniques allow you to do that today. Then we have this guy. He's actually not a philosopher, he's a filmmaker, Spike Jonze. And he said that our subjectivity is so completely our own. And now I want to bring in subjectivity as well, because like I said earlier, the compression of reality into some sort of language or description of it is actually done by someone. Someone has to actually do this. And naturally, that description will become flavored by the person who is doing this. So not only do we have all this other complications to deal with, we also have subjectivity in the picture, because it may very well be the case that if I put two different people to provide a description of the exact same event, I find it very unlikely that their descriptions would match 100%. So there's likely to be as many descriptions of reality as you put people into actually describing the same event. So that's also an aspect that's really important when you look at information modeling. It's all subjective in the way it's captured. So given all these complications that we have when we want to store information about reality, and the fact that if we are aware of that we lose some fidelity, what should we actually record about reality when we try to record stuff or document it? Well, Voltaire, he said that one should always aim at being interesting rather than exact. And I think this is a very good motto, because if you are going to capture events happening in reality, I think it's much more important to actually focus on capturing not everything and not to infinite precision, but actually capture enough of that event to have something that is in the end interesting. Your description should be useful. So this is really something that you should strive for all the time, I think. Try to be interesting rather than exact, because it's sort of a fine line in between the two. But I think too much effort are put into actually being exact when it would have been sufficient to be interesting. So we can probably capture a lot of interesting information, even though reality is as untangible as it actually is. So once we have information, we have these things, and Leibniz said this thing that if there's at least one property that differs, they are different things. But there's also something more abstract that we work with, and that is classification. So once you start to have more than one thing that you look at, like several things, you can start to notice similarities. So they become relevant when you have many things. And if you start to look at the similarities, it may make sense to actually group these things into some sort of groupings. And this is typically what lots of modeling techniques do today. You start with classes of some sort, and that's your fundamental building block when you create models. And as we will see later, I'm not so sure that that is actually the most fundamental way you can do it. But this poet said, James Whitcomb Riley, he said he has something that has later been known as the duck test. And what he said was that if it quacks like a duck, looks like a duck, and walks like a duck, I'm going to call it a duck. So basically, and this is quite profound actually, because what he's saying is that if some object exhibits some certain characteristics, then I'm going to classify it because of that. So classification is sort of a subset or some properties that an object needs to have. And if it has those properties, then we can say that this thing belongs to a certain class. So classification is basically just groupings of properties, which is something that we also will make use of later in transitional modeling. Then, of course, when it comes to classification, we also have to keep in mind that this too is subjective. Here's a tile salesperson. He's holding up what may look like a Rolex, and he's claiming that it's same but different. And of course, in a sense, maybe it would go by as a Rolex, even if it is a fake. Still, there are differences in how we want to classify things depending on the use cases or whatever. So classification is in itself context dependent and subjective. And this is something that we very rarely think about, particularly since most modeling techniques start out with the classification as the building blocks. So you start by actually working with something that you want to be universally understood and unchanging over time, but they are not, in fact. So, given what we've said so far, we can ask ourselves, when is a thing actually a thing? So if you look at this image here, on the far left you can see this big blur, and you can question yourself, is that blur a thing? And I usually say that my definition of when a thing is a thing, that's when something is sufficiently distinguishable from something else to be told apart. So in the case of the blur, it's definitely the case that we can see it, because you all know what I'm referring to when I'm talking about it. So even if we cannot really say where the edge of the blur is, where it sort of transitions and becomes the background, it doesn't really matter, because we can still identify this blur, because somehow we have the ability to actually tell it apart from something else, and the background in this case. And of course, is that a thing for you if you were to create a model and capture reality? Well, it certainly depends on your requirements, but let's say that that blur is something that the Hubble telescope picked up on one of its images. Could be absolutely super important. So I'm pretty sure that most blurs that the Hubble telescope picks up are actually deemed worthy of being things. Then again, if you work in an industry producing maybe something you would hang in your Christmas tree, then those things that are furthest to the right could be the only things that are worthy of being deemed things in your case. Maybe the other ones are stuff that you actually produce the things to the right of. And that brings us to the next one. This could be actually the same thing and not different things. It could be like, this is the formation of a thing. So over time, this gradually may become what you see on the right-hand side. So the blur becomes these two adjoined balls. And then you also have to determine, well, again, sampling, at what moments do I want to capture information about this process? How much information do you want to store about this process? And yeah, so this is a further complication, or something that you often have to deal with, particularly in manufacturing. So given this philosophical background, if we were now to create some sort of modeling technique based upon this philosophy, what would sort of be the cornerstones of that modeling technique? Well, first, we could recognize that things in themselves are, of course, important, because at the very core, this is what we actually store in our database. It's things in the end that are going to be stored, and maybe relationships, information about relationships that they have. We know that the properties that things have are important, so we need to have some way of capturing those. We also probably would like to have classification as something that is ephemeral, which means that it's something that can change over time. It's sort of volatile or yeah, ephemeral is probably the right word for it. So it's something that's non-lasting. It's something that can change. It's something that we can have subjective opinions about. We also have to take into account that values are always imprecise. We cannot measure anything with infinite precision. So we should have some way to deal with that situation. We also know that one way of dealing with something that is continuously changing is to actually use sampling to capture, rather than to capture the actual continuous thing, we capture transitions between states or something, versions, moment to moment. When it comes to changes, it would also be nice if we could make as few assumptions as possible and just say that the identity of a thing is the only thing that is immutable, that can't change over time. And we will let everything else about a thing being possible to actually change it over time. So every other property that a thing may have apart from its identity is something that can change over time. And of course, given that this, whatever language or modeling technique we're now building, we have to remember also that it records statements about reality. It doesn't record reality itself. So we need to be able to work with statements about reality. And of course, things in reality, they fold out one way or another. So there is some sort of truth in reality itself, because you can say whether or not the thing actually happened one way or another if from the perspective of a reality, but not from the perspective of an observer. For any observer observing reality, that certainty that reality has is always interpreted and subjectively determined. So we absolutely need to be able to work with uncertainty in this modeling technique some way. And we also know that as soon as subjectivity is involved, it could be the case that you need to change your mind. Let's say that I'm a witness of a crime and the police come and interrogate me, and I'm a little bit flustered because I just witnessed something, and they ask, and I say, well, I'm absolutely sure that the perpetrator left in a Volvo when he drove away. But then when I later think about it, I realized that, oh, wait a minute, I was wrong. It wasn't actually a Volvo. It was a Toyota instead, because I got it wrong in the heat of the moment. So then I need to be able to revise my statement. So opinions may of course change over time as well, and we need to have that in mind. And finally, of course, if we are going to have some sort of communication, or whatever my document of reality is, it should have some sort of purpose, that some other person is going to come and look at this document of reality and actually understand something. But wouldn't it be nice if we could keep the number of things that needs to be agreed upon small, so as small as possible actually. So it's interesting to ask yourself, what is the smallest amount of things that you need to agree upon in order to have sort of a fruitful conversation, or that I could pass on a documentation of reality to you and you could actually read and understand it, given that there are some very minor or a small number of things that we absolutely need to interpret exactly the same way. Now, with that in mind, let us then look at transitional modeling. And this is a modeling technique in which we actually try to abide by what was said on the previous slide. We try to capture as much as we can and have as few things as possible that you have to agree upon, which means you can disagree about just about everything else. Transitional modeling builds upon one construct, and the construct is called a posit. And you can see the structure actually of the posit below here. So it is it's actually a triple, but it's unlike the triples that you find in it's not a semantic triple. This is something else. It just happens to have 3 positions, so that's why it's a triple also. The first position is a set, followed by 2 other positions, which are not sets. So what are those things then that you find in a posit? We're going to build everything in transitional modeling using posits. So a posit, it looks like this. It has a set first in its first position. It's called the appearance set. It consists of appearances. An appearance is an ordered pair of an identity and a role. Identity is the identity of a thing. I usually think of, in theory, an identity is an abstract property that the thing has that is unique for that thing. No other thing has the same identity. So in practice, when you store information in a database, this would be maybe a unique identifier. Those look a bit like hexadecimal strings, or it could be something as simple as just an integer from some sequence, where you ensure that no other thing can have the same integer number. In the examples today, we will use just integers for the identities. The role, this is the role that this thing is playing in this posit. I'm going to get back to that. So after this appearance set, there is a value. And in the examples today, we will look at primitive values like numbers or strings. But this could very well be a structured value, like a combination of a number of strings and integers or something. So it could be a structure. May also be something, we talked about the imprecision, so it could be something that is imprecise that we store here also. It could be a range, for example, or it could be some other way to express a fuzzy value. And finally, in the last position, you find a time point. This is what we call the appearance time point. So if we go back to that philosophy of momentariness, this is sort of what you would do when you take a snapshot of reality and sample it. There's some time point at which you take this snapshot of reality, and you find some value that is appearing in reality. But in order for this value to appear, it has to be connected to one or more things. That's the only way this value can appear. And when it appears for these things, it appears also when this thing is playing some particular role. So this will probably become more clear when we look at some examples. But first, we talked about what you need to agree upon. And the good thing here is that in transitional modeling, the only thing 2 different interpreters of the stored information will have to agree upon are the appearances. So if something has the identity 42, it should be crystal clear to the other person also that what this 42 refers to. And of course, that could possibly be deduced by the information itself, but that deduction has to be possible to make anyway for 2 different interpreters of the information. And then you have the roles. You will see some examples later, but let's say a role is husband. So if you have the husband role and you have a string there saying husband, this should also this also needs to mean the same thing for both interpreters. They should understand this role as being representing the same thing in reality. Of course, again, with some detective skills, it could be possible anyway to deduce what it could be. I mean, we have been able to decode lost languages later on thanks to smart detective work. So that's possible. Then again, these are the smallest number of things that you actually need to agree upon. The good thing about that is this makes it possible to actually disagree about everything else, which is quite nice, because that means we can be quite opinionated and flavorful in the things we can express using transitional modeling. So here's the first example. The appearance set in this case has two appearances. There's something with identity 42, which is the husband, and there's something with identity 43, which is the wife. And in this case, the value that appears for these two is the value married. And this appears since the 19th of June 2004. So that's the way you should interpret this posit. Not that difficult to understand what it represents. It represents a marriage. So when the appearance set has more than one appearance in it, like this, where it has two, the posit is of a relational nature. It expresses something, a relationship of some sort between the things that are involved. And in this relationship, the things have different roles. But the appearance set can also contain just a single appearance, and in that case, the posits become attribute-like instead. So in this case, you have the identity 42 and the name with the value Lars Samuelsson since the 20th of August 1972. You also have another posit 42 and hair color, and the value is gray. And this is a future value. It's on the 22nd of February 2022. And this is also important to remember, that a lot of statements about reality they don't have to be about things that are in the past. Could be future things as well. And this is much more common than you may believe. I mean, most companies and businesses know already before Black Friday what prices their products will get on Black Friday, or how large the rebates will be on Black Friday. So you often determine things in advance, schedule meetings, etc., etc. A lot of the world is pre-scheduled anyway. Then it may not turn out to be the case when you actually pass those points in times, but it's quite possible to have lots of statements about something in the future anyway. So we cannot or should not avoid those. And we will see later, but these are actually just pieces of information, just statements. And they in themselves actually in transitional modeling have no truth value. So this is just a piece of information that we are later on going to have opinions about. So these could be completely true or completely untrue. You can still actually store them in a transitional model. So they are just pieces of information, just statements. Of course, they usually come from somewhere, but they are just statements anyway. No truth value in themselves. Using these, we can actually define what change is. So in the first case here, you can see that the same appearance set is appearing twice in the first and second posit. That's the 42 and name. But there's a difference in the time points and values. So change is actually defined as when the same appearance set can be found in another posit, but with a later appearance time and a different value. Then this different value constitutes a change. So it's quite nice that you can actually define what change is. And the same thing goes here for the hair color. So it's been brown since 1973 and is expected to turn gray in 2022. And that's actually my name before I got married. I changed my name when I got married. So I used to be Lars Samuelsson, and since 2005 I'm Lars Rönnbäck instead. So if you look at the appearances here that are the same ones, 42 and name, and you have this change of the name from 1972 to 2005, we can start to talk about a timeline. You can put those values onto a timeline, making it visually possible to determine when one value was in effect and when a new value came into effect, replacing the old one. And it's possible to produce such timelines for any appearance set, and we call these appearance timelines. And these are important later on, because one of the important things is to actually find which value was in effect at a certain point in time. A transitional modeled database sort of becomes like a time machine, making it possible to travel back to a point in time and see which value was in effect at that point in time. And then these appearance timelines become important because you need to travel to a particular point on that timeline. So let's look at a few of the things that we have so far. We had my name, Lars Rönnbäck, there, and we had the hair color, gray. What we haven't talked about so far is what type of thing this number 42 is. What is this thing that has a name and a hair color? And this is when we come to the point where classification is introduced into transitional modeling. And just like anything else in transitional modeling, a classification is also a posit of a particular type. So first, we create this new thing with identity 4711. It also has a name, and the name of this thing happens to be person. And let's say that we introduced this thing in 2019. Now, the only thing we need to do in order to indicate that number 42 is of this class 4711 is by actually introducing a relational posit. And in this case, we indicate it by the roles these things play in this relationship. So in this case, we have something that is the thing, number 42, and the class, which is 4711. So this sort of binds person to the thing that has identity 42. And as all other relational posits, this one also has a value. And we can say that this is the active classification since 1972. And I am going to distinguish this type of data a little bit from, but usually we talk about data or information about information. We call it metadata. I'm going to call this peridata instead, because I will reserve metadata for something else that we will see later. Peridata, it's something, it's peripheral data, data sort of more attached to the original data. And what we can do also is to actually reserve these rows, not necessarily in theory, but let's say that we want to have some sort of more widespread or universal agreement upon these things, these roles, then it would be good to reserve them. Let's say that I'm going to build a database based on transitional modeling. Then these would correspond to sort of reserved words, sort of what you would find in SQL as well. So these would be reserved words in the database language. So the peridata sort of helps you flesh out the context around the things that you're working with in your model. And for example, and it's sort of determinable by the domain itself. So if I were to ask someone, well, when you said something had gray hair, what did you say it was? Was that a dog? And then someone could actually say, being in the domain, say, no, it's a person. It's Lars I'm talking about. So that's basically what peridata is. And classification is one type of peridata that you can do in transitional modeling. The good thing about actually the classification being posits themselves is that just as any other posit, it becomes possible later on to actually have opinions about this, as we will see. So I mentioned metadata, so let's start to move towards metadata as well. So we have these posits here. We have Lars Rambäck, the name of this thing, and the hair color gray. And we also had the additional information about this thing 42 being married to 43, where 43 is the wife of 42, so it's the husband. So first, what you've noticed perhaps is that we're not distinguishing here between the posits that behave like attributes and the posits that are of a relational nature. And the way I see it is that a relationship is actually, we treat them as an attribute as well. So a relationship is just like an attribute. The only difference is that it takes more than one thing for this attribute to take on a value. So whereas the hair color of a person, it takes just one person to determine the hair color of a person. Whereas to be married, it's a value. It's also sort of an attribute, but this attribute takes on, it needs two persons in order for it to appear. So when you have posits, in order to be able to produce metadata, we need to be able to talk about the posits, like information about information or data about data. So to have metadata, we need to be able to talk about the posits themselves. And in order to do so, we actually create identities for the posits themselves. Just like number 42 is the identity of a person, 555 here is the identity of a posit. So let's give these three posits three unique identities. And once we have these identities, we can create posits in which these identities appear. So, for example, and one of the most important type of metadata posits that we will have is the assertion. And an assertion is when you have the identity of a posit in a relational new posit. An assertion is in itself a posit. So as you can see down there, we're saying something about 555. 42, that thing, that's the person, it's me. I'm ascertaining the posit with identity 555, and what I'm doing is I'm assigning a certainty to that posit. So that is my opinion about this posit. How, you could say, well, loosely speaking, how true do I believe this posit is? And that's the certainty. And in this case, I'm not entirely sure that my name is Lars Rönnbäck since 1972. So perhaps I should be, but let's say for the sake of reasoning here that I'm not. So it's 90%. Of course, assertions are also made at certain points in time. So this will have an assertion time point as well. So I am doing this assertion or ascertaining the posit in 2019 on the 20th of October. So assertions are the way that we can actually express opinions about posits. As we will see, it is possible for me to state a few things about these three posits that we've seen now, and I'm going to say something here now. I'm going to ascertain them with different certainties. So let's take a moment and look at what these different certainties actually mean. And the first thing we can notice is that we're actually going to be allowing negative certainty. And this was a consequence that sort of popped out of the theory that it was actually possible to talk about something with negative certainty. And this has an interesting meaning. So the first one is the 90%, the one that we saw on the previous slide. So we can move on to the next one, which is the one about my hair color. So what does it actually mean if I'm asserting that with minus 80% certainty? Well, what that means is that I'm actually stating something about the opposite of this posit. So I'm believing with 80% certainty that the opposite of this posit is true, that my hair color will not turn gray in 2022. So using negative certainties, we can actually talk about opposites. And if you think about it, this is something that is quite hard to do in traditional databases. There's really no way to store an opposite value. So the trick here is to actually have these opinions with negative certainties instead, where you keep like the positive value instead in the posit. So looking at it, I think there's quite a few use cases because in the real world, it's quite common that people express statements where they actually talk about opposites of things. Like, well, I'm absolutely sure that the thief didn't come in through the window. So you're actually expressing an opposite. Then we have also the possibility to express something using 0% certainty. So everything in the interval from minus 100% to plus 100% is possible, including 0. And 0 is complete uncertainty. And what that means is you have absolutely no idea whatsoever if this is the case or not, what the posit is stating. So in the case of posit 557 here, which is the marriage one, what I'm saying here, my opinion is that I have absolutely no clue whether this is true or false. And one of the things you may think here is, or think about is there a difference if I were to say with minus 100%, that ascertaining this posit with minus 100%. And the difference is that if I'm stating something with minus 100%, I'm saying that I'm absolutely sure it's not the case. And there's actually a difference there, because if I'm saying that something is absolutely not the case, that has more informational value than actually saying I have absolutely no idea, because when you say it's absolutely not the case, I'm ruling out one alternative. So it's possible for me actually to state for a lot of alternatives that I'm absolutely 100% sure that's not the case. So for every time I'm doing that, I'm actually ruling out one alternative, which means that it has to be one of the other ones. Whereas if I'm stating that with 0% certainty for a number of posits, it still could be either one of them. So this is where it might get a little bit tricky to visualize it or think about it, because there is sort of a nice symmetry here between what you can state and what you cannot state before you start to contradict yourself. And we have this described quite well in our paper, so I'm not going to go into the details here, but it is possible, if you have information stored in a transitional database, either to enforce that you cannot produce inconsistencies, or you could, if you allow it, search the database for anyone who starts to produce inconsistent opinions. And if you look at it, it's symmetrical as well, this certainty. So if I'm stating with negative 80% certainty that something is not the case, that also means that there's a 20% chance that it actually is the case. So ascertaining something with negative 80%, I could just as well have described as stating it with 20% certainty instead. Okay, so let's look at a change here then. So here we have, it could be a change. Here we have two different statements, posits, about the marriage. And as soon as something in a posit is different, then it's a different posit. So it needs a new identity. So these two posits have two different identities, 557 and 558. Because they contain different time points. And we can tell sort of a story by looking at different assertions down here. So the first two ones are made on the 20th of October 2019, and they're made by two different persons, 42 and 43. 42 is actually stating that this person is 90% sure that the first posit is correct, whereas the other person is absolutely certain it's not the case. And perhaps these two persons, being married, went home and discussed this and came to the conclusion that something was not right. Because the next day, on the 21st of October, you can see that number 42, that person is now stating that the first posit has 0 certainty. So they are changing their opinion about the first posit from being 90% sure the day before to being 0% now. And as you can see, both are now in complete agreement instead of posit 558, because they are 100% certain that is the case. So changing opinions over time is also possible, and just as with the appearance timeline, you can create an assertion timeline, and in this case it's the same thing. If it's the same appearance set and you have a different certainty with a later point in time, your opinions have changed. And this assertion timeline also is important, because this is the way that you actually do corrections. So that is something that often happens with information. You have information stored, but somehow you realize that something is not correct. A name was misspelled, a color was wrong or something like that, or the point in time when something was supposed to have appeared was actually also turned out to be wrong, so you need to move that time point. And because these corrections can affect both values and time, so the assertion timeline is sort of orthogonal to the appearance timeline. They are two different timelines. And in that case, when you want to travel back in time, you have these two time points now that you have to take into account. I want to travel back in time to see which value was in effect, but I also can, if I want to, travel back to a point in time before any corrections were made, or rather to a point in time and see what were different persons' opinions at that point in time. So you can travel back both over versions and over opinions. Of course, you could have stated instead, when you do a correction, I could have stated with minus, instead of saying 0% there in the middle assertion, it would have been possible to say minus 100%, to say I'm absolutely certain it wasn't in 2004, now that I'm certain it is in 2005. So that actually, from a theoretical perspective, that would be sort of equivalent, but it turns out that in practice it becomes more manageable if you perform corrections using this 0% certainty instead. You have less data to take into account later on. So, assertion, one type of important metadata. Another type of metadata that you normally store if you build like a data warehouse. A data warehouse integrates data from many different sources, usually through some sort of batches. These days it's often micro batches, like every 5 minutes or something you get new information. And it's often beneficial to know from where your data came and how it came into the database. So what you can also create is metadata for which, in this case, which job produced this posit in the database. And in this case, you can see it was a job with identity 2001. It was successful. And once you have this identity of the job, you can start to add context about the job itself. So you can have a lot of posits talking about the actual job, when it was started, which user started it, etc., etc. And it's only your imagination that limits what information you want to store as metadata about your posits. And of course, assertions and other types of metadata since they are posits, you can give them identities too, and you can start to talk about metadata if you like. So you can have opinions about opinions, and you can do that like layers upon layers if you need. Probably the number of use cases for that will quickly dwindle down as you add layers, but I'm sure there are cases where opinions about opinions, for example, can be useful. So from here, it's actually possible, and this is something that we do in the theory of transitional modeling, to produce constraints, for example, cardinality constraints of relationships. They are also posits. We can produce information about identifiers, like what are the natural keys or natural ways to identify something. They are also posits. We can talk about structures, like we had this classification, which we saw was more or less just a tagging of putting a name on this thing that had identity 42 and saying it's a person. But we can also talk about what the actual structure of a person looks like. Which types of posits does a person contain? Well, we could say that it's something that has a name, it has a hair color, and so on. That's also possible to define using posits. And there are many other things as well, like inheritance between different classes. We can talk about trustworthiness, consensus, if many people have the same opinion. Contradictions is, like I said earlier, it's possible to actually deduce if someone is contradicting themselves in their opinions or not, and so on. So many things you can do with posits alone. Now let us look at some of the implications when you start doing transitional modeling compared to traditional modeling techniques. I said earlier that the smallest or the least amount of things that you need to agree upon are the appearances. So basically what you are modeling in a transitional model are the roles that can appear in the appearances in posits. So classification, which is normally the starting point of traditional modeling techniques, sort of become second-hand class citizens. They are not the first-class citizens that you're used to. And this took some time for me to get my head around. I mean, I come from a background in information modeling where it's so natural to start with classes, the types of things that you're going to be working with, and you build your model with those as your building blocks. In transitional modeling, classification is ephemeral, so it's opinionated, subjective, so it's something that you can't really start with. It's something that becomes a part of your model instead as peridata. So in transitional modeling, you have to start with the roles. So how do you then actually produce models when you do not have access to the classes? And I had to get my head around this and think about this. If there was some way, because we also used to visualize our models in some way, and I thought it would be nice if there was some sort of visualization at least of how to do modeling in a transitional model, apart from just having a list of the roles and their descriptions, because that's of course one way of doing it. Since classification is opinionated, and it's also possible we defined one class for the number 42, which was person, but could also have been multiple classifications in effect at the same time. I could just as easily at the same time add teacher or student or whatever. So I can have like an infinite number of classifications if I want to. Probably not in a finite database, but anyway, you get the idea. So I coined the term schemaful databases, because transitional databases, they become practically full of schemas. And I think this is actually quite great, because the more I think about it, the more sure I am that classification is something which is definitely not unique and universal. I mean, it's both subjective and, for the most part, the same thing can be classified in many different ways. So let's take a little look at this. This is sort of a reaction also against all the talk that has been over the last few years about schema-less databases. So I thought schema-full was a nice contrary to that. So what I was thinking was that let's start by actually putting the roles down on a piece of whiteboard like this. So these are some roles that you can find within a transitional model. Now, if we are to speak about classification, then there has to be more than one thing, so you can actually start to talk about similarities. If there's just one single thing you're looking at, there's actually no need for a classification at all. So in order for classification to become relevant, you have to have, well, lots of things and figure out their similarities. So you've probably seen these maps, geographical maps, where they have lines for heights. So everything that is within the same line boundary has the same height. So we're going to use that analogy, but instead of height, we're going to have the number of things that have these roles. So in this case, if you look at this one with the lines, you can see here that there are 1,450 things that has a beard color, but they also have everything else that is contained within that boundary. So 1,450 things have a beard color, a name, a hair color, a height, and a social security number. So if we move closer to the center, there are more things that have height, social security number, name, and hair color. 5,000 things have all those 4 roles. Whereas even more, 5,800 things have a name and a hair color. And as you can see here, there are also 750 things that have a name, a hair color, and an RFID tag. So in transitional modeling, roles can be sort of reused between classes. Now that we have these, we can start to think about what can we classify these as. We also have some lines down to a relational posit there, so you can see the roles that you find in a relational posit, and that's the role of being an owner and the role of being a pet. So that could perhaps give you some sort of clue to what this could be. So one possible classification, and remember this is just an opinion, could be that we have this person class defined as that which has a beard color, height, social security number, name, and a hair color. But as you remember, there were fewer things that had a beard color than had the other roles. So that doesn't necessarily mean that person is a bad or not appropriate classification. Of course, you can create a classification in which not everything has all of the roles. I mean, the way you look at it, if you have a person class, and a person class is quite commonly found in many models, there will be both men and women in there, and the women won't have a beard color. And we still can't treat them as parts of the person class. And on the right-hand side, you find the animal class, which we can define as those things that have an RFID tag and a name and a hair color. And the interesting thing here is, of course, also when you start to think about how you could query a transitional modeled database, you could actually do queries like give me everything that is named Lars, and you could get results regardless of if it's a person or an animal. Or you could say, give me everything that has a hair color, and you would get both persons and animals. So you can ask for anything that has or appeared in a certain role. Give me everything that has appeared together with hair color. So the querying is actually quite wide and flexible compared to what you could do, for example, in a transitional model database. And what we've done in our research is to look at what types of queries you could actually do here. And as it turns out, you can do queries that looks like name value pair databases. You can do queries that are resemble the types of queries you can do in graph databases. You can do queries that resemble those you do in relational databases. So it's really interesting, and there's a possibility to have lots of interesting features in a transitional modeled database, and types of queries that you couldn't that you normally couldn't do in a different database. Now, I'd like to talk a little bit about how we can use transitional modeling to express other modeling techniques. And of course, one of the techniques is the one I mentioned at the beginning of the presentation, anchor modeling, which is the technique that we've developed together with Stockholm University. The team involved is me, my colleague Olle Regart, the professor Paul Johannesson, Petja, she moved to Australia and she's working in the private sector there now. Maria is still at the university, so those are the ones who've been involved with anchor modeling and the research. And the graph that you see here on the right-hand side, this is what an anchor model looks like visually. So we have a graphical notation, and that notation is a derivative of entity relationship modeling. So for those of you who have seen entity relationship models, you will recognize the symbols, where we have some extensions to the symbols. And I will talk about them just on the next few slides. So in anchor modeling, we have this central concept called an anchor. And the first thing we can note is that anchor modeling is a modeling technique in which you start with the classifications or the classes that you have. So we have one anchor for every class that you have. So person in this case would be a typical anchor that you find in anchor modeling. So it is a traditional modeling technique in that sense. And these anchors, they hold the identities of the things that belong to that class. So in this case, you would find the number 42, it would be residing in this anchor because it is belonging to the person class. That also means that in anchor modeling, the classification itself or the model is treated as something that is universal, so you cannot have opinions about the model itself. It is what it is. Around the anchor, we find attributes that belong to that anchor. So in the case of a person, what types of attributes can we find? Yes, well, we can find the name and the hair color. And these will become two different attributes in the anchor model. So the role that you have in transitional modeling will become the name of the attribute itself. So later on, when they become tables, they will become the table name in the database. So an attribute is constructed by holding a foreign key reference to the identity. So that number 42 will be found also in the attribute together with the actual value. And in this case, it would be Lars Rönnbäck for the name attribute and Gray for the hair color attribute. There's two types of attributes that we distinguish in anchor modeling. In transitional modeling, there's a time point connected to everything. Whereas in anchor modeling, you can actually say that you have a static attribute. And in that case, you won't be storing the time point at all because you're assuming that this is an attribute that absolutely under no circumstances can change over time. If an attribute can change over time, this is visually distinguished by having a second outline around the attribute, so you get the symbol at the bottom. And in that case, a time point is also stored in the attribute itself. We also have a concept called knots in anchor modeling, and they are similar to a lookup or a reference table, or if you look at it more formally, they are an enumeration of values. So what they are used for is to constrain the possible values in an attribute to a particular set of values. So in the case of hair color, for example, maybe you have 20 different possible colors that you can pick from, and no other colors should be allowed there. So in that case, it makes sense to constrain the values to that set of 20 different values. So then you would use this construction of a knot. And theoretically, if you compare this to an entity relationship diagram, in the traditional sense, a knot is actually equivalent to a construction of having an anchor with a single static attribute. So they are equivalent from a modeling perspective. Whereas I believe that the fact that we have this distinguished symbol for knots in anchor modeling makes it visually very easy to determine when something is constrained to a limited number of values and when they are not. There's also some performance implications. A knot actually helps with the performance in the database, because let's say you have 1 million persons that you need to store the hair color of. Storing a string value 1 million times is quite inefficient. So if you can store say a small value, a tiny int or something instead, and look up what that corresponds to in the enumeration, that is becomes much more efficient. And of course, in transitional modeling, what does it actually mean then? Well, the gray that we find here in transitional modeling, then gray would actually be a value in an enumeration. If you remember, I said early on in the presentation that the values that you find within posits, they can be of primitive types like strings and integers and so on, but they could also be of a structured type. So in that case, you would have a structured data type that is an enumeration in transitional modeling. Then finally, we have the tie. The tie represents a relationship in anchor modeling. So this will be corresponding to the relational posits in transitional modeling. And a tie just contains foreign keys to the anchors that is adjoined to the tie. So in the case of the first one here, there's a lecturer and an invoice, and that would produce a tie where actually the roles become part of the name of the tie. If we were to look at the different columns within the tie, we also actually name the columns in the resulting table by the names of the roles as well. So it's easy to see what is what when you look at the foreign keys in a tie. Ties also come in two flavors depending on if they are static, so it's a relationship that under no circumstances can change over time, or if it's a relationship that actually can change over time, like the marriage. It's quite possible that at some later point in time these two people become divorced. Hopefully not, because it's me and my wife. So that's the way you model relationships in anchor modeling. Now, what we didn't look at so far is the actual value. As you can see, there's no blue circle here around the values. So how do you actually manage that within a tie? So for the static tie, it's actually, we're going to assume, since it cannot change, that it has some sort of implicit value that we never actually need to talk about. Whereas for the husband-wife thing, we need to be able to capture also what state this relationship is in. So in order to do that, you can actually put a knot on a tie. And normally we only allow relationships between anchors, but since a knot is theoretically equivalent to an anchor with a single static attribute, it's actually allowed to put a knot on a tie directly. So that's the only reason you can put knots on ties. So in this case, there would be an enumeration of the possible states that this relationship can be in. So it would contain values like married and divorced, maybe single or something before you're married, widowed, whatever. And in this case, the tie contains the appearances together with the appearance time point, and the adjoined knot contains the value of the current value of the state. And we also talked a little bit about metadata. Depending on your requirements and the use cases of the data, it may be relevant or it may be irrelevant to have metadata. So if you use I haven't talked about it yet, but we have this online modeling tool in which you can actually build these graphical models, anchor models, and with a button click you can generate code that actually implements this model into a target database. But there are, of course, some options, and one of the options is to actually use metadata. So if you use metadata in an anchor model, it will actually create an additional reference in every resulting table that can point to a metadata structure in which you can, well, you can build a separate model just for metadata and capture whatever you need. And so far, when we've talked now about anchor modeling, and you saw the symbols that we had for with the double outlines and without the double outline, and depending on if you want to store the appearance time or not. So we've talked about if values can change or not. That is only appearance time. We've only supported appearance time when we've talked about it, and the way that we distinguish these graphical symbols only has to do with appearance time as well. But from transitional modeling, we also saw that there was this other timeline that was important, which is the timeline over which we change our opinion about things. Corrections, for example, typical. So in that case, we can actually switch on support in this tool to generate something called concurrent reliance temporal anchor modeling. Quite a tongue twister, but that's what it's called. And when you switch on concurrent reliance temporal anchor modeling, you actually add support for having the possibility to express that different persons have different opinions about things, and these opinions can also change over time. As it turns out, anchor models, they are built on top of the relational model, so the resulting implementations become implementations in a relational database, at least for now. So that also means that we need to somehow maintain integrity in the database, and particularly temporal integrity, which means that well, two values shouldn't be able to be in effect, two different values shouldn't be able to be in effect at the same time. My hair color, for example, it can't be both brown and gray at the same time. There has to be one definite value. That's temporal integrity. And as it turns out, you cannot maintain temporal integrity for two orthogonal timelines in a single table. So the only way you can maintain this temporal integrity is by breaking those two timelines apart and putting them in different tables. So basically, in concurrent reliance temporal anchor modeling, we have two tables. We have one table storing the posits and another table in which we store the opinions about these posits. They are called the annex tables in anchor modeling. All right, so that was how we can express anchor modeling using transitional modeling. Now let us look at another popular modeling technique, which is semantic triples. Most of them are expressed in a language called RDF, Resource Description Framework. And that's the one we will be looking at here. This is quite different because now we have left relational databases. Now we're into the domain of graph databases instead. In graph databases, you store information. You stop thinking about tables. Instead, you think about nodes and edges. So your things sort of become nodes in a graph, and these things are connected to each other through edges. And you can name the things and you can name the edges. And this will become your information model instead. So there's an example here of a person called Bob who's interested in the Mona Lisa. That was created by Leonardo da Vinci. Bob is a person. He's born on 14th of June July 1990, and it's a friend of Alice. So we will be looking a little bit closer in this model and see how we can express it using transitional modeling. So in essence, RDF is also described using triples, and they look something like what you see above here. Bob is a person. So if you look at that statement, it's divided into three parts constituting a triple. The first part is called the subject, the middle part is called the predicate, and the final part is called the object. So it's subject, predicate, object in an RDF triple. There are some more examples here that Bob is a friend of Alice, and Bob is born on the 4th of July, 1990. Three different statements. In order to manage identification or identities, RDF uses something called uniform resource identifiers, and they look like a URL that you can type into a web browser, more or less. So you can see those identities represented on the two final rows, where you have the identity of Bob and the identity of Alice. So let's see how we can do a transitional representation of this information. As you can see, it's quite liberate in what you can create. You can have quite complex statements within the predicate, for example. So RDF is quite liberate in the types of constructions that you actually can make. So in transitional modeling, we have to use the identities. So we will first express that Bob belongs to the class person. So we're going to use the Bob identity, and then we have some identity for the person class as well. And then we have, so in the appearance set, you can find Bob as a thing and person as a class. And this connection is active since some date, because everything is temporal in transitional modeling, so you have to actually specify those things. And the second one, that he's a friend of Alice, we have Bob appearing in the role of being the friend, and Alice as the one who is befriended of, in that case. So we have the identities of them, and their friendship is active since some point in time as well. And let's see, then we have the one where Bob is born on the 4th of July, which is another one, which is the identity again, but now it's a attribute-like appearance. So there's just one appearance in the appearance set. So is born on, and the value is the 4th of July 1990, and this is also since some date, probably also since the 4th of July 1990. And finally, we have the names of these people. So that identity of Bob is known as Bob, and the identity of Alice is known as Alice. So it's basically their names. So that's the way we would represent it in transitional modeling. So you can see it's quite a direct translation between the two. And you remember those green words we had that I called reserved roles within transitional modeling. There's also some reserved predicates and stuff in RDF, and they call it a vocabulary. So we have something in transitional modeling corresponding to a vocabulary in RDF, and that's our reserved roles. So let's move on to the next slide. Using that vocabulary, you can express things. That person, for example, is a class, and that is a friend of is a property, and you can also constrain this relationship of friendship so that it's only valid between persons. So it has a domain of person and a range of person. So that is basically a constraint of this relationship. And of course, we can do something like that in transitional modeling as well. So we can first state that the type of this person identity is class. A type of, let's take another one, we have a dog as well. It's also a class. And then we can create constraints within transitional modeling as well by actually saying then that person is a friend of person is a property, but it's also possible for a dog to be a friend of a person. So it's quite easy also to express constraints within transitional modeling. Then, of course, if we were to build a database engine that uses these transitional modeling constructs at its core, it would be up to the database engine to actually enforce constraints like these. The way they're stated right now, they're just informative, but you may also want to actually enforce certain constraints when you work with storing information in a database. And in RDFs, you can also limit or qualify a predicate so that it becomes more specific. And in this case, they're actually making is a friend of a bit more specific by expressing it as is a good friend of. So is a good friend of is a sub-property of is a friend of. So a good friend of will apply to less people than is a friend of. So we can do this in transitional modeling as well. But this is something that we will have to do sort of on the metadata layer, where we can relate different constraints to each other. So in the first case here, we have this restriction is a good friend of, and then we have the less restricted one, which is a friend of. And if we give these two posits their own identities, 901 and 902, we can express the fact that 901 is a constraint or a restriction of 902. So it is possible, again, to do this type of construction within transitional modeling. Now, for those of you who want to get some more information about transitional modeling, I'll show you a few places where you can find some additional resources. And transitional modeling is just one of the things that I'm involved with when it comes both to practical implementations and scientific research. So there's other things you may be interested in as well. Almost all of these things can actually be found on our homepage, which is anchormodeling.com. When you first come to that page, you will see that it has like a blog-like structure, but there are some categories on the left-hand side on the pages section with links to different parts of the site. And one of them is a link to something called publications, and that's where we try to publish everything that we do, all our papers, all our presentations, video tutorials, recordings, etc. You can find there. One of the things you can find there when it comes to transitional modeling is a paper called Modeling Conflicting, Unreliable and Varying Information, which contains the first description we made of transitional modeling. The only thing there is that we are actually not using posits for everything. Assertions in that paper had a little bit of a different structure. But now we actually express assertions as posits as well. Everything is posits now. There's also other things you can find there that could be of interest. We took some of ideas from this and actually incorporated into dimensional modeling to create a variation of that called temporal dimensional modeling, in which we don't have to use any slowly changing dimensions, or rather maybe have a different type of slowly changing dimension, which circumvents a lot of the issues you can find with the various types of slowly changing dimensions you have today. So this is one place where you will find a lot of information about this. I also post a lot of information on LinkedIn, but most of that I actually cross-post also on the Anchor modeling site. We also, as I mentioned, built a modeling tool for Anchor modeling, which is also available from that very same homepage. This is just a screenshot of what it looks like, but you build models in something that looks much like entity relationship diagrams. Well, you saw a few of these earlier when we were doing the mapping between Anchor modeling and transitional modeling. So Anchor modeling is right now in a state where you can produce basically three types of models. You can have unitemporal. Then it's basically just the posits. You can have bitemporal, which means you add assertions, but you don't really store opinions or uncertainties. It's just one opinion, the one of the database, and it's your posits are only considered true or false over positing over the assertion time. Then you have concurrent reliance temporal, which adds more features like opinions and uncertainty also into the resulting implementations. So if you want to check that out, have a go at the online modeler. You can generate code there that will actually produce implementations in a few different target databases as well. We also wrote a ELT framework for actually loading data into a Anchor model. Can be used with some other modeling technique as well. It's also open source and available on GitHub. It's based on Sisula, which is short for Simple Substitution Language. It's a templating language that we developed ourselves because at the time, this was quite a few years ago, there weren't really that many templating languages available. So now there's handlebars and mustache and stuff like that. But so this is built using that. There are some video tutorials and things available for that too. And finally, like I said, I do post quite a few things on LinkedIn. That's also where you usually can find information about different conferences and events where I speak. So you can connect with me or follow me on LinkedIn in order to be notified about when stuff like that happens. And I try to see LinkedIn as sort of a knowledge sharing platform, so I do my best to write articles and posts with that intent. And that's about it for this presentation, and I hope you enjoyed it and that transitional modeling is something that you have gotten a little bit more familiar with. Thank you very much.